Imagine a world where time isn't just a constant ticking clock but something that can stretch, shrink, or even stop entirely. Can time travel really be possible? What if you could travel forward or backward in time, witnessing events yet to happen or even changing the past? Is time as we experience it truly the same for everyone, or is it something far more mysterious, depending on where we are or how fast we move? Can we ever escape the grasp of time, or are we forever bound to its relentless flow? Or perhaps, could the answers to these questions unlock the possibility of traveling through time itself? How close are we to achieving something that, just a century ago, would have seemed impossible? 1. Nature of time. Time, in its most fundamental form, is a concept that we use to measure the sequence of events and the intervals between them. However, time is far from being as simple as it may seem at first glance. The understanding of time has evolved considerably, from the classical notions established by Isaac Newton to the groundbreaking discoveries made by Albert Einstein. The nature of time is one of the most profound mysteries in modern physics, with its behavior closely tied to the concepts of space, motion, and the fabric of the universe itself. 2. The classical view of time. Newtonian time. Under Sir Isaac Newton's classical mechanics, time was considered absolute, meaning that time passed uniformly and independently of the events or objects within the universe. In this framework, time existed as a separate, linear, and unchanging entity, ticking away the same for all observers regardless of their motion or position in space. This idea of time was integral to understanding the motion of objects and the laws of physics as they applied to everyday experiences. However, as scientists began to explore the universe in greater detail, they realized that time could not be as simple as Newton had suggested. The uniformity of time was shattered with the advent of relativity. 3. Einstein's theory of relativity. A new understanding of time. Albert Einstein's theory of relativity fundamentally altered our understanding of time. The theory is split into two main components: special relativity and general relativity. Both of these theories provide insights into how time behaves under different conditions, specifically under the influence of high velocities and strong gravitational fields. Special relativity. Time dilation and the speed of light. In 1905, Einstein introduced the theory of special relativity, which revolutionized our understanding of space and time. One of the key implications of this theory is that time is not absolute. It is relative, depending on the observer's state of motion. Time dilation. According to special relativity, time slows down for objects moving at speeds close to the speed of light. This effect, known as time dilation, means that a clock moving at high velocity will appear to tick slower compared to a clock at rest. For example, if a person were to travel on a spaceship at nearly the speed of light, their perception of time would be different from someone who remained on Earth. While the person in the spaceship would experience only a few hours or days of travel, years could pass for the person on Earth. This has been confirmed through experiments with atomic clocks on planes and satellites. The speed of light. Special relativity also established that the speed of light is constant for all observers, regardless of their motion. This uniformity of light's speed underpins the entire theory and leads to the time dilation effect. As objects approach the speed of light, time behaves in increasingly strange and counterintuitive ways. General relativity. Gravity and time. Einstein's general theory of relativity, published in 1915, further expanded on the concept of time by introducing the idea that time is affected by gravity. In fact, time is part of the spacetime continuum, a four-dimensional fabric that combines the three spatial dimensions with time. Gravitational time dilation. According to general relativity, time passes more slowly near massive objects. The stronger the gravitational field, the slower time moves relative to areas with weaker gravitational fields. This effect is most pronounced near extremely dense objects, such as black holes. In practical terms, this means that clocks at the surface of Earth tick slightly slower compared to clocks in orbit around the Earth, where the gravitational field is weaker. This phenomenon has been observed in experiments involving precise measurements of time using atomic clocks in space and on the Earth's surface. 4. Can time be changed? From the perspective of Einstein's theories, time can be altered or changed, but only under extreme conditions, such as traveling near the speed of light or experiencing intense gravitational fields. While we cannot manipulate time at will, these discoveries suggest that time is not a fixed, immutable flow but something that can bend and stretch under the influence of motion and gravity. The ability to manipulate time, however, remains theoretical and is not something that can be achieved with current technology or understanding. Yet, the concept of altering time continues to captivate scientists and theorists. Can we travel through time? The idea of time travel has fascinated humans for centuries, from science fiction novels to modern-day physics research. The concept hinges on the possibility of moving backward or forward in time beyond the normal flow that we experience. Physicists have explored several theories and models that may offer glimpses of how time travel could theoretically occur. 1. Time travel to the future. Time travel to the future is relatively more straightforward within the framework of Einstein's theories. According to special relativity, as an object approaches the speed of light, time for that object slows down relative to an observer who remains stationary. This means that a person traveling at near light speeds would experience less time passing for them compared to someone who remains stationary on Earth. However, time dilation at such speeds is only practically achievable with objects that are either traveling at nearly the speed of light or have access to technologies that could potentially manipulate velocity on a grand scale. Currently, we do not have the technology to build spaceships that could approach such speeds. 2. Time travel to the past. The theoretical possibilities traveling back in time, however, is a far more controversial and speculative topic in physics. Several theoretical models have been proposed, but none have been proven or shown to be physically feasible. Wormholes, Einstein-Rosen bridges. One potential method for traveling through time is the concept of wormholes, also known as Einstein-Rosen bridges. Wormholes are theoretical passages through spacetime that could connect distant points in space and time. In essence, a wormhole could provide a shortcut between two different regions of the universe, potentially allowing for time travel. Traversable wormholes. The idea is that if we could find or create a stable wormhole, it might allow for travel from one point in time to another. However, the problem lies in the fact that wormholes would require exotic matter with negative energy to keep them open. No such material has been discovered, and wormholes themselves remain purely theoretical. Closed time-like curves. Another possibility for time travel to the past comes from closed time-like curves, CTCs, which are paths in spacetime that loop back on themselves. If an object were to travel along a CTC, it could theoretically return to its earlier position in spacetime, essentially allowing for time travel into the past. Grandfather paradox. A major issue with time travel to the past is the so-called grandfather paradox, which arises when a traveler alters events in the past that would prevent their own existence. For example, if a person were to travel back in time and prevent their grandfather from meeting their grandmother, it would create a paradox in which the traveler could never have been born to travel back in time in the first place. Cosmic strings. Another possible mechanism for time travel involves cosmic strings, hypothetical one-dimensional defects in spacetime that may have formed in the early universe. These strings are thought to be incredibly dense and have a gravitational pull strong enough to bend spacetime. If two cosmic strings were to pass close to each other, their combined gravitational forces could theoretically create conditions where time loops or closed time-like curves could occur. 3. The practical challenges of time travel. Despite the theoretical possibilities, time travel remains an unresolved issue in physics. The primary difficulty lies in the immense energies and conditions required to manipulate spacetime, which are far beyond our current technological capabilities. Additionally, many of the theories, such as wormholes and cosmic strings, remain purely speculative without any empirical evidence. 4. Quantum mechanics and time travel. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, also offers intriguing possibilities for time travel. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that every quantum event could branch into different possible outcomes, creating multiple timelines. While this does not directly imply time travel, It raises questions about the nature of reality and whether there could be alternate timelines or parallel universes where events unfold differently. 5. Conclusion. The future of time and time travel. While the concept of time travel captures the imagination and has a rich history in science fiction, the practical reality of traveling through time remains elusive. Current understanding of time, as outlined by the theories of relativity and quantum mechanics, suggests that time is not a fixed and absolute entity but something that can be manipulated under extreme conditions. However, the prospect of time travel to the future is more plausible, at least in principle, while traveling back in time presents far more profound challenges. As our understanding of the universe and the laws of physics deepens, we may one day discover new ways to explore and perhaps even manipulate time, opening up possibilities that currently exist only in theory. These questions open the door to one of the most fascinating and mind-bending areas of physics. Join us as we explore the very nature of time itself, and consider whether the impossible might one day become possible.